Hello everyone, this is Priyosha. Welcome to my presentation about load balancing and virtual machine allocation in Docker and Kubernetes. Let's understand what is load balancing. A load balancer is used to distribute the traffic across multiple servers, which are collectively called as server cluster. So why do we need load balancing? If any website can be accessed by thousands of users at a time, and this will cause heavy load on servers. Due to this, sometimes the systems may crash. To prevent this, we need load balancing. Load balancing will manage the incoming traffic by distributing the available resources and decreases workload among virtual machines in an efficient way. Now, load balancers can be of two types: physical server and virtual server. Virtual servers are similar to traditional servers in which both require an operating system and applications to perform. But virtual servers provide server experience without the need to be physically on site. If we see, these days many companies are shifting to virtual server because of various advantages like uptime, security, cost savings and easy recovery. Let's see what is uptime. Physical servers will have constant downtime due to maintenance. If the production site was hit by any disaster, it is essential to quickly restore the data with minimum downtime. Like, it can also take several hours or days for physical server to restore because it needs a whole new setup of installing an operating system, setting up applications and restoring critical data from backups. But in virtual servers, it can be recovered easily, like from the previously created virtual machine backups, resulting in almost zero downtime. Let's see the next reason: security. The security management is more easily configurable in virtual server environment than in a physical one. With physical servers, you have to build a system of protection for each individual server depending on its computing capabilities and resources and the sensitivity of data that it stores. Now, this can be a resource intensive task if the IT infrastructure is built upon 10 or more physical layers. On the other hand, a virtual server environment can be protected on the basis of universal security model. All the security policies and procedures can be developed, documented and implemented from a single point. The next reason is savings. The building and maintaining a physical server environment can be quite expensive because of constant hardware and software upgrades. At the same time, virtualization is considered a perfect option for enterprises which contain a large number of servers. A virtual server environment allows us to evenly distribute the computing resources among all running virtual machines. This ensures capacity optimization for a less price or a minimal price. The next reason is easy recovery of the data. Because of the abstraction layer between the physical hardware and the virtual server, backup software has evolved to back up the entire virtual server as a whole container. Now, this not only provides greater protection but also faster restores when it really matters. We can go back to an exact working image from the time the backup was taken and not have to worry about minor details that are so often overlooked when trying to rebuild a server. Okay, so now as we've seen physical and virtual server, let's see the types of servers virtualization. In traditional virtualization, each virtual machine contains a guest operating system, a virtual copy of the hardware that the operating system requires to run, along with an application and its associated libraries and dependencies. Now, instead of virtualizing the underlying hardware, we use containers to virtualize the operating system. Here, the containers sit on top of a physical server and its host operating system, like for example Linux or Windows. Each container shares the host operating system kernel and contains only the application and its libraries and dependencies. Here, the absence of guest OS makes the containers very lightweight, fast and portable. Let's see the containers more in detail. What is a container? Like a container is a standard unit of software that packages up code and all its dependencies so the application runs quickly and reliably from one computing environment to another. Containers have become integral part of development process. With the increased widespread use of containers, multiple container environments have become common and hence load balancers are becoming a necessity to distribute traffic and reduce server load. These days, if we see, containers are being used in Docker and Kubernetes. This helps the process of creation, deployment, and running of applications in different platforms much easier. One of the major purposes of using Docker and Kubernetes is utilizing the load balancing capabilities. And also, we can use multiple container environments. And now with multiple container environments becoming widespread, load balancers are becoming a necessity to distribute traffic and reduce server load. We have different load balancing algorithms to provide a solution based on the efficiency. Therefore, load balancing these containers can help not only the utilization of server resources but also it enhances the efficiency of the entire development process. Let's see what is Docker and where containers are used in Docker. Docker is an open source tool developed to make the process of creation, development and running of applications in different platforms much easier. It provides a toolset to easily create container images of applications. In Docker, images become containers when they run in Docker engine. If we have a Docker file that is a shell script that defines all the tasks that need to be executed. From the Docker file, if we build, we get a Docker image, and from the Docker image, when we run it, we get a Docker container. The Docker container image is a lightweight, it is a standalone and can be executable package of software that includes everything needed to run an application like the runtime, the code, the system tools, the libraries and all the settings. As we have seen Docker and container, let's see how the load balancing happens in Docker. There are basically two types of load balancing in Docker, that is internal and external. So let's see about internal load balancing. Internal is all about load balancing requests that are made from within the Swarm cluster, whereas external load balancing targets ingress traffic that enters a cluster. Now here ingress means the request coming from the end user. Both of these functionalities are provided by the Docker engine itself. Let's understand the Docker Swarm load balancing, that is internal load balancing, in detail. Now this feature is automatically enabled once a service is created. So when a service is created, it gets a virtual IP address right away on the service network. When a service is requested, the resulting domain name server query is forwarded to the Docker engine, which in turn returns the IP address of the service. Now this returned IP address is called as virtual IP address. The traffic sent to that virtual IP address is load balanced to all of the healthy containers of the services on that particular network. All of the load balancing is done by Docker since only one entry point is given to the client. That is it has only one IP address. Now let's see about external load balancing. In Swarm, every node listens on the exposed port and then forwards this request to the exposed service virtual IP address using a special overlay network called as ingress. The external load balancer happens to forward the request to only one node that does not have service instance. Now this request is handled and forwarded by IP virtual service, which is done using ingress network, completing the load balancing cycle. There is a routing mesh available in the ingress network capable of routing 7-layer traffic. Now this is done by inspecting the HTTP header of the request, thus operating at an application level. Now this feature is called as HTTP routing mesh, which allows each created service to be accessed to a DNS label. Let's understand the internal and external load balancing by taking an example. Now, in the given figure, let's consider this as an Amazon ecosystem which will have different external services from the end user coming, and also it will have internal services in between the Amazon like the booking system, the payment system, refund system, catalog system, and so on. The Docker Swarm load balancer runs on every node and can load balance requests across any of the containers on any of the hosts in the cluster. The Swarm load balancer handles inbound client requests, which is external requests represented in green arrows. This is called when end user is placing an order. Now here the red arrows represent internal service to service requests. As we mentioned before, they may be calls between the booking, payment, or refund systems. The internal call between these services will be managed by the internal load balancer. One of the major purposes of using Docker Swarm is because of the functionality of both internal and external load balancing within the Docker engine. But there are no additional features like content-based routing, control authorization, and any security features. And Swarm load balancer is actually a basic 4-layer load balancer. Now, many real-time applications require other extra additional features like security and access control authorization and content-based routing. To add these features, we add Nginx to the load balancer. Let's see load balancing using Nginx. Now here Nginx is a web server that is used as a reverse proxy, HTTP cache and load balancer. It is used to build high concurrency and low memory using an asynchronous approach in which requests are executed by a single thread rather than creation of a new process for each web request. Nginx is an open source load balancer which gives extra critical features which is not provided in the Docker engine itself. Now the features that are provided by Nginx are: Nginx will provide a choice of load balancing algorithms for the user. And also it gives more protocols like for example HTTP and WebSocket. And it also gives configurable logging. And it also gives scripting for advanced use cases like using Lua, Perl or JavaScript. It also has traffic limits including request rate, bandwidth and connections. Now, the simplest way to use Nginx open source is to deploy it as a service with one or more containers. The necessary ports for the Nginx service are exposed on the cluster, and the Swarm load balancers distribute requests on these ports to the Nginx containers. Let's understand by using an example. Now, in the given figure, we are deploying Nginx in two containers as a service. The services A and B are deployed on more than one server and in multiple containers. Swarm assigns a virtual IP address to service A for use inside the cluster. Now, Nginx uses this virtual IP address during configuration of routing instead of the individual container IP addresses. Now, when a client makes a request for service A to the first Swarm node, the Swarm load balancer on that node routes the request to Nginx. Now what the Nginx will do here is the Nginx will process the request and routes it to the virtual IP for service A. The Swarm load balancer routes the request to one of the containers for service A on any of the Swarm nodes. Nginx will also take care of both internal and external load balancing. As we have seen what is Docker and how load balancing happens in Docker, let's see about Kubernetes. Now, Kubernetes is developed and maintained by Google. It is portable, extensible, open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. Now, the Kubernetes will make use of images made by the Docker. Compared with other virtual machines, Kubernetes provides more accessible, efficient, and faster way to convey administrations and applications. We have to start the containers at the appropriate time, find out how the containers communicate with each other, and store them appropriately. Now, Kubernetes will solve this problem very efficiently. Let's see briefly about the Kubernetes architecture. It contains a master node. A master node is the first and most vital component, which is responsible for the management of Kubernetes cluster. It is the entry point for all kinds of administrative tasks. There might be more than one master node in the cluster to check for fault tolerance. The next is scheduler. The scheduler schedules the task to the slave node. It stores the resource usage information for every slave node. It is responsible for distributing the workload. The pods. A pod is a combination of single or multiple containers that logically run together on nodes. There is also a Docker container which is running in each of the worker nodes, which runs the configured pods. Now kubeproxy. Kubeproxy acts as a load balancer and network proxy to perform service on a single worker node. Kubelet. Now this gets the configuration of a pod from the API server and ensures that the described containers are up and they are running always. Let's understand how load balancing happens in Kubernetes. The load distribution that exists in Kubernetes operates through kubeproxy feature. Services in Kubernetes use virtual IP address which the kubeproxy feature manages. The kubeproxy default mode called IP tables enables sophisticated rule-based IP management. In IP tables mode, random selection is a native method for load distribution. In this situation, an upcoming request goes to one of the service pods that is randomly chosen. Now here, the ingress load balancer for Kubernetes offers the most flexible and popular method as well as cloud service-based load balancing controllers and other tools for ingress from service providers and other third parties. The ingress offers the most popular method. It operates using a controller with an ingress resource and a daemon. Here, the daemon sets are another specialized form of pod controller that runs a copy of a pod on every node in the cluster. This type of pod controller is an effective method for deploying pods that allows us to perform maintenance and offer services for the nodes themselves. The ingress resource is a set of rules governing traffic. The daemon applies the rules inside a specialized Kubernetes pod. Now the ingress controller, it has its own sophisticated capabilities and built-in features for load balancing, and this can be customized for any specific vendors or systems. There are many varieties of ingress controllers with various features and a range of plugins for ingress controllers such as cert managers that provision SSL certificates automatically. Let's see about the algorithms and load balancer strategies provided by Kubernetes. There are a number of Kubernetes load balancer strategies and algorithms for managing external traffic, like round robin, L4 round robin, L7 round robin, and consistent hashing. Let's see about round robin load balancing. In a round robin method, a sequence of eligible servers receive new connection in order. This algorithm is static. It means that it does not account for varying speeds or performance issues of individual servers. So a slow server and a better performing server will still receive an equal number of connections. Next, L4 round robin load balancing. It is the most basic default Kubernetes load balancing strategy in a typical Kubernetes cluster that comes from the kubeproxy. However, because a kubeproxy is actually a process rather than a proxy, it uses IP tables rules to implement a virtual IP address for the service, adding architecture and complexity to the routing. Let's see about the L7 round robin load balancing. Now, this is used to bypass a queue proxy. The load balancer tracks the availability of pods with the endpoints API. When it receives a request for a specific service, the load balancer sorts in order or round robins the request among relevant Kubernetes pods for the service. Next is consistent hashing or also ring hash. In consistent hashing algorithms, the Kubernetes load balancer distributes new connections across the servers using a hash that is based on a specified key. It is best for load balancing large numbers of cache servers with dynamic content. Now, this algorithm is inherently combines with the load balancing and persistence. As we have seen load balancing in both Docker and Kubernetes, let's compare them both. Docker Swarm can be used for a simple architecture, but whereas Kubernetes provides a load balancing techniques for a very complex architecture. Kubernetes has inbuilt load balancers and ingress with n number of load balancing strategies that can be implemented according to the architecture. Whereas in Docker Swarm, if we want to automate the ingress traffic, we need to go for an external open source load balancers such as Nginx. Here, Kubernetes uses a flat networking model in which all pods can communicate with each other and communication can be restricted via network policies. But whereas in Swarm cluster, each node generates an overlay network for services that are available to the entire cluster. The Kubernetes has built-in high availability and healing of failed nodes, whereas Docker Swarm's high availability is mainly based on the ability to clone services such as Swarm nodes. The Kubernetes pods can expose services externally and it performs load balancing for each service in the cluster, typically using an ingress. Whereas in Docker Swarm uses DNS to distribute incoming requests to service names. It can automatically assign addresses to services or the user can specify specific ports for the services to run on. To conclude, we can use the container-based systems based on the technical architecture of the firm and the complexities of the services.